Now friends, in the previous lecture we took the concept of torsion, and in this lecture I will try to take the concept of torsion forward. Now, I had two circular cross section, right? I had this portion of the shaft which was effectively nothing but was equal to dx, and if I applied some kind of a shearing stress tau, then this AB plane moved to AB dash, and there was some kind of a shearing strain at this point, right, which is essentially equal to tan of this. Suppose this angle is delta, so tan of delta, suppose. Now the shearing stress or tau was directly proportional to this, and the shearing strain was effectively equal to BB dash by AB. And what was this BB dash? BB dash was essentially equal to, if this is R suppose, and this if it was d phi, so this was equal to R d phi by dx. And this d phi by dx is actually the angle of twist that this shaft undergoes with respect to x. So this is equal to R into theta, but theta is the angle of twist per unit length. So this is equal to gr theta, and we have this relation. Now from the previous lecture we also had an assumption that every circular cross section will remain circular. What does that mean? If suppose I have a diameter AB in that circular cross section, and if after torsion it has moved to suppose A dash B dash, there is a change of angle, right, and that is theta 1. I have suppose another diameter CD, and this CD has moved to C dash G dash. There is also a change of angle of this, and that is theta 2. Then effectively, if the circular cross sections were to remain circular, then this change of this angle will be equal, that is theta 1 will be equal to theta 2, right. So if we take this concept and if we apply it here, we can say that at every point, any point in the circular cross section will be guided by this relation. So essentially tau will be equal to, tau at any point in this circular cross section will be equal to g into rho into theta, where rho is the distance of any point from the center. So if rho is this is delta, this angle, this is delta, right. So if rho is this, so essentially I have g rho into theta. Now this rho, if it's at the center, if I'm going to find the shear stress at the center, this rho will be equal to 0, and essentially tau will be equal to 0. And if I'm going to find the shear stress at the outer surface, this rho will be equal to R, and this tau will be equal to tau max will be equal to g into R into theta. So essentially there will be some kind of a stress distribution within a circular cross section, and that if we study it is like this. If this are my axis, and this, if suppose this is a circular cross section, and I cut the portion about this axis, then if I draw the shear stress distribution, then it will be some kind of a linear stress distribution, wherein at this point this will be 0, and at this point it will have the maximum shear stress. Now essentially these are the horizontal shear stress that are developing parallel to the cross section. There will also be certain vertical shear stresses that will develop perpendicular to the cross section. So essentially this will be a linear function of theta of R, because as the radius changes, this tau will change, and effectively this tau will be directly proportional to R. Now the next objective of ours would be to find out the relation of this shear stress distribution with respect to torque. And how can we do that? Let us see. For example, if I rub this thing out, then we have this T to be equal to the integration. For example, if this is suppose an area dA, and the distance of this area dA from the center of the shaft is suppose equal to rho, right, and tau is effectively the shear stress acting on this area. So tau into dA into rho will basically give me the moment of this area, right, moment of the shear force of this area with respect to the center of the shaft or the axis of the shaft. And essentially an integration of this will be equal to the torque that I applied. So we know that tau is nothing but is equal to g into rho into theta into rho into dA, right. So essentially g theta, if we take it out, is equal to rho squared dA, or g theta j. Now what is this J? J is nothing but the polar moment of inertia, right? And that is equal to rho square into dA, right? And for a circular cross section, as we all know that moment of inertia about any axis is same and is equal to pi d to the power 4 by 64. So J is nothing but the summation of the moment of inertia about two axes, about two perpendicular axes. Let it be any two perpendicular axes. And effectively this will be equal to 2i then, and 2 into pi d to the power 4 by 64 is equal to pi d to the power 4 by 32. So g theta pi d to the power 4 by 32 is is the value of t for a circular cross section. The next thing I'm going to do is I'm going to find out the value of theta. What is theta basically? Theta is the angle of twist per unit length of the shaft. So this value of theta will be essentially equal to T by Gj, right? So this is the angle of twist per unit length of the shaft. So if I'm going to find out the total angle of twist, then if suppose that is theta t, then theta into L will basically give me the total angle of twist. So theta into L, that is TL by Gj, will give me the total angle of twist. So this is one relation I have found out from this lecture, number 3. This is one relation, number 4. And the first two relations were tau is equal to G into rho into theta, derived from the previous lecture, number 1. And T is equal to nothing but is equal to Gj into theta. This is essentially this, but I will write it in terms of T, so I'm giving it equation number 2. Now, the next thing is to find out what will be the maximum value of this tau, right? The tau will have its maximum value when gr into theta t, right? And theta t, or this, or not theta t, theta will be equal to t by gj. Gg cancels out, it will be tr by j. So effectively, I have certain important relations